you very much for the kind invitation and kind introduction. Okay, I'm going to talk a little bit about clocks today. Oops, sorry for shooting in the face with a laser. So I'm going to talk about clocks in general and use our clock lineage a little bit as an example for this. So let me start with a sort of introduction and question. So, how do you measure time? Typically, when we measure time, chronological time, what we mean is we are looking at some sort of periodic process, something like an oscillation of a pendulum or the rotations of either the Earth around the Sun or the Earth around its axis. And so we count these periodic events and we use that to assign time intervals. There are also biological substrates that are related to the passage of time, and one of them is shown here, tree rings, right? You get a different ring every year, so every time the seasons change, you get a tree ring laid down. So you can look at the pattern that is left behind in the organism to infer the amount of time that has passed. And then, of course, in theoretical physics, the time itself is defined by entropy as the direction in which the entropy in the universe increases. So there's an entropic time component that essentially says, the past is the more ordered state of the universe as a whole. And so these things here are chronological time, and we also call it wall clock time or calendar time. And the important thing that maybe has become clear in the last few years is that fundamentally biological time is not the same as calendar time, or biological age isn't the same as calendar age. And I'm going to use a slightly, humorous, maybe not anymore because Val Kilmer died this year, but I'm using this example here, which is, two actors, Val Kilmer and Tom Cruise, who in 1986 were both in their early 20s and very biologically similar, right? So they were both young actors, who could be romantic leads or fighter pilots, and so they're obviously in a very similar biological state. They're a highly resilient state. However, time passed the same for them, but biological time clearly did not. So if you look at Tom Cruise at 60 and Val Kilmer at 62, their relative age difference chronologically hasn't changed at 2 years, but their biological age difference is quite large. And in fact, Val Kilmer just died, and Tom Cruise is just releasing more movies where he's hanging outside of planes and jumping motorcycles into, off mountains and stuff like that. So there's a big biological difference in their state now. And so this is, of course, due to a number of factors that we all know. So one is genetics. So if you go to your doctor and you say, why am I not doing as well as Tom Cruise? Then they might say, well, he has lucky genes. It's also due to lifestyle, right? So, it is, of course, the job of a Hollywood actor to look good and stay young. And so, there's a lot of lifestyle differences between, my average day and his average day, I'm sure. It's also due to environment. So we know environmental exposure can have a large effect, and disease. And then it's, however, and that's an important point, also due to stochasticity, to randomness, to luck. And also due to stochasticity. And then, of course, it's due to stochasticity. And I'm making this point here because actually these factors, if you look carefully, have less of an impact than you might expect on individual aging trajectories. There's a lot of very small, subtle effects, dynamic effects that can affect long-term life trajectories that aren't easily tracked to like a SNP or a gene. And so the goal, of course, is to eventually have an intentional impact here. Can we actually, make our trajectories maybe look more like this? Early on in life by doing the right things early, and can we find ways of knowing what it would take individually to do this? And so that is kind of the mission of an aging clock. So this is a review where Sarah Heck showed this nicely, that there's a big difference, but this would be the perfect correlation between chronological age and biological age, and then people increasingly separate as they age. So what then are biological aging clocks? And so they're basically algorithms. They're algorithms that use some sort of observable feature of the biological system to then assign the true biological age. Okay, so and I put true in citation marks here because what do we even mean by this, right? And I'm going to get back to that in a second. So, but the idea is we have features, and it could be something like a transcripts, DNA methylation, lipids, proteins, or clinical features, clinical markers, faces. We then use some machine learning AI, if you want to be fancy today, algorithm, and as Peter Fedishev would say, math here only for intimidation purposes only, right? So this is just illustrating what I mean, some sort of model, and then I give a true biological age. That's the sort of mission and the idea. And of course, the methylation clocks were the first example of something like this. They got a lot of attention and was very successful. But the problem is, what do I actually want to train to? Because if you know anything about machine learning, it's fine, you have an input space, but you then need a ground truth. You need something to train your model to, right? What are you training the model to? What is the thing that your training data has that allows you to predict this? And there isn't really a magic way of measuring true biological age. We don't yet have a good clock. We don't have a Star Trek tricorder that you can point at somebody and it tells you what their true biological age is. So we don't know the ground truth, so how can we train these clocks? And so one idea, which might be quite obvious, is we could just go and use chronological age, right? So because I have a lot of samples and they all have a label, they all know, okay, I know this person was 50 and this person was 67 and this person was 25. And so it seems natural to say, I'm going to build a model that looks at the biological features in this blood sample or in this DNA methylation data set, and then I'm going to predict the chronological age. And so the idea is, if some sort of feature, I have the known chronological age, and then I build a training loop, and I essentially make a model that goes very well from these features to this chronological age. And then I get something like this, where I have chronological age here, biological age there, and I have a nice regression here, like a straight line, and there's a relatively good performance. I can evaluate how good this is by taking the root mean error here. And then I say, okay, so this guy here has a chronological age that is a lot higher than his biological age. So obviously, being 25 biologically but 40 chronologically means that this person is biologically younger than their chronological age. So that's good. That's where you want to be. That would be your Tom Cruise story. Or I go and say, okay, this person is above the line, so their chronological age is smaller than their biological age, so they're biologically older. And a lot of clocks today are built this way, and that's because that data is readily available and you can build models that do that. But there's a bit of a methodological problem with this, and that is that if I look at the residual here, and I'm saying, okay, so that's my biological age delta, then that's also my model error, right? Because when I'm trying to build a model, what I'm trying to do is make that residual 0. So how do I know whether that's how much of that error is the biological age difference that's true, and that is the model error, or that's the model error and that's the biological age difference that's true? It's really no easy way to knowing whether my residual is due to my model being imperfect or my data being noisy, or it's due to the fact that these people actually have a chronological age that's different from their biological age. So if to push that point, what if I have more data? If I get 10 times more data and a fancier algorithm, make a better model, I go and I let the model select the perfect features from my large data set to make a good aging clock, I might end up training something like tree rings, because in a tree I can do this very readily. I look through here, I know exactly when this tree was planted or grown, right? So this is now completely possible to say the tree is this old, okay? But then I get a perfect model, which is great, right? So this model now performs optimally. It performs almost flawlessly, giving me the chronological age of the sample. So it's a perfect model. But for the purposes I just discussed, it's also perfectly useless, because now it doesn't actually tell me anything about the biological to chronological aging differences. So if I build models and I take this approach to its extreme, I eventually end up with a perfectly useless model. Maybe has a, for police work or something, I can take a sample and know exactly all of it. But it doesn't do the thing I want it to do. So how can I do better? What can I train to? And this is where, I've been giving talks about Gompertz, British actuary, imperial times, Victorian actuary for a long time. But fundamentally, what he discovered is that your risk of dying doubles every 8 years. So when age goes up by 1 8-year interval, then your risk of dying doubles, okay? So risk of dying doubles every 8 years. And so what that looks like is like this, which is a bit scary, right? Say you start with a risk of dying of 1 in 10,000. Then after 40 years, it becomes 1 in 600. And after 60 years, it becomes 1 in 100. And after 80 years, it's about 1 in 20. So your risk of dying really goes up quite dramatically. And that's why you don't see any people 150 years old, because you're basically reach 1. But so this is a very strong biological pattern. And if I made mortality rate doubling time 10 years instead of 8 years, it would have quite a lot of difference on the risk of dying. And so this would be a dramatic impact, for instance, on population aging by only having a sort of 20% difference in aging rate. Right? Now, at this point, people always say, okay, yeah, fine, you want to train to mortality, but who cares about mortality? It's all about health span now, right? It's health span is the thing. But the truth is, if you die of old age, you die of resilience failure. You don't really die of magically running out of life force, right? So mortality is driven by age-dependent mortality is driven by a reduction in resilience. So you fall, you break something, you die, you get a virus, for instance, COVID or the flu, you get pneumonia, you die. So many causes of death in the aged is due to resilience failure. And that's highly related to function. And then the rest is due to age-dependent diseases. So in other words, if we are having an effect like this, or we're measuring differences in mortality, we are catching differences in disease risk and differences in resilience and therefore in function. So actually, by training to mortality, you're really training to aging, because the causes of aging are all the things that we're trying to manipulate when we talk about health span. Okay? So the idea is build mortality predicting clocks. Okay, so how does it work? So we take some feature space and then we do a risk equivalent age. In other words, we are training to the probability of dying based on features. And in our case, we built this based on clinical features. And the reason for doing this, there's several, but one of the major reasons for doing this is that that data is readily available. There are data sets where people measured standard clinical chemistry and then followed people for 20 years. So in other words, I have the ability to look at mortality over 20 years, right? Which is not that many data sets that you can do that in. Okay, so let me show you how this works. Okay, so I'm going to speed through this. You could do this with any one of these feature spaces, and the argument for this, or one of the arguments for this, is that all of these features are highly correlated. When one of these things fails and goes out of regulations, everything does. So you could do this from methylation, you could do this from lipids, when we have trained clocks on all sorts of input spaces, even facial features you can use. Okay, so let's do this. Let's have a look what that looks like. And we're going to use linear dimensionality reduction by SVD or PCA. I'm going to keep this very short. Principal component analysis to reduce the amount of the complexity of the data by looking at, basically major vectors in the data, PCs. And that's why we call it lineage, because this is all linear. So there's a linear risk model and the linear dimensionality reduction, right? So you could do a non-lin age or a deep age by doing this with neural networks, but we're trying to prove that you can do this fundamentally by doing the simplest thing, and that's doing it with all linear tools we can fully understand. Okay, so why principal components? Well, principal components give you major axes in your data. So in this case, you have two things that are related. And you find the major axis of covariance, and then you rotate your coordinate system so that your first axis aligns with the major axis of covariance. Don't worry if you don't quite follow this. It's basically just saying all that PCAs are rotations of the coordinate system. It's a very simple transformation. And so, for instance, if the features have meaning, like in this case, say this is cholesterol, and this is blood pressure, then of course if you have both high cholesterol and high blood pressure, your risk of dying is much higher than if you have both of them low. And if you only have high cholesterol but good blood pressure, or high blood pressure and good cholesterol, your risk is intermediate, right? So this now means that this new axis here has some sort of interpretable meaning. For instance, you can call it cardiovascular disease risk. So PCs are much more interpretable. Well, maybe not, we'll discuss that in the lab, but then, for instance, latent variables of nonlinear tools like neural networks or autoencoders or transformers. So it's a simple way of doing that thing and being still able to follow what it does. Okay, and they can do surprising things. This is a really fun data set where there's a SNPs, single nucleotide polymorphisms, in the DNA of Europeans, and if you just do the PCA of a giant SNP data set, you basically get the map of Europe back. So the major PCs are essentially north, south, east, west directions of Europe. So you can learn about the geographic distribution of people's ancestry simply by doing the first two PCs of the data, right? So just to illustrate, PCs can do cool stuff. And this is a data set from my lab, or Nicholas' lab, our labs, where we did PC on some transcriptional data in flies. So they're male and female flies, and they're between 5 and 50 days old. And so the first PC is sex. So male flies are quite different from female flies, but then you get a very strong signal for aging. So even there, you can do a transcriptional clock immediately just by taking the first PC and like using a linear model of this. So they're good at picking up these sort of trends if you have a good aging cohort. Okay, so what do? We take NHANES data, which has all the standard stuff that you care about, like blood pressure and exam data, some questionnaires, clinical laboratory blood pressure, all of these things. And it has 20 years of follow-up, so we know what happens to these people. So we took the 99, 2000, and 2001, 2002 data sets because they have the longest follow-up time. Then we did the PCA, so we reduced these high dimensional space into lower dimensional space. And for instance, PC1, as you can see here, this is age and this is PC1. It does exactly what you expect. There's more variance, people become more dissimilar from each other, and it increases with age. So that's something that you would expect from an aging pattern. And then we take about 17 of these PCs and we make a model, a risk model that predicts death. And so this is what that looks like. You can interpret them, these rotations, you can look at the axis and you can, for instance, identify which parameters contribute how much to each PC. So you can do a post-analysis. 1 minute left, okay. All right, let me just not do that. Okay, so just to show you quickly that it works, so you put the input data, you do your model, and then you predict the biological age, and the people down here are biologically younger, and the people here are biologically older. And this now is not model error. These are differences in the predicted risk of dying, right, which I can now compare in the data to true survival. And so how does it work? If I look at these guys here, they're biologically younger. The model says you are going to die later. And you look at 20-year follow-up, you take 65 to 74-year-olds, you get 60% of them survive the next 20 years. This is real survival data, so if you follow these people for 20 years, 60% of the people that are biologically significantly younger will survive for 20 years, which means they survive into their late 80s. If you take the opposite group, the people up here, only 10% survive this period of time. So the risk of dying is substantially higher if the clock puts a larger age on you, which is why the reason for this is obvious. We are expressing risk as age. Okay, and it works better than the methylation clocks. GRIM-H2 is pretty much the best DNA methylation clock for predicting mortality, and we are a little bit better, quite similar, and we are quite a lot better than most of the methylation clocks that are not trained to mortality, which is not a surprise because the task we're giving ourselves is to predict mortality, right? Okay, so then I'm going to skip this. I'm just going to just say people are also have higher cognitive performance. This comes back to the point that mortality tracks physiological aging. So if you're biologically younger, you have a better cognitive performance score. You're also walking faster, and you're actually retiring later. So these mortality predictors also predict outcomes over the next 20 years, like that. And just to make the case that, yes, there are no clocks that are perfect, because, for instance, in the oldest age bins, the performance drops. So if you're old enough, if you're at the 10, 20% mortality per year, 80-year-old, actually the performance of the clock is much worse. And that's probably because entropic aging at this point is a very strong component, and we have probably not 100% handle on this. So we're working on ways to address this. Okay, so this is, I'm going to not do this because it's already late. Just the last thing here is, if you do this in different data sets, for instance, in UK Biobank and in NHANES, you actually get a very strong conservation of these PCs. So my point is, this is not private to this NHANES data set, because the question is always, does it work in Singapore? So this is the correlation plot, which basically shows that the first PC in NHANES and Biobank is almost exactly the same vector. Right? So these patterns are universal biological patterns of human aging. They're not something specific to that data set by and large. Stuff starts blurring out back here. Okay, and that's me. Thank you very much. Sorry I ran over a little bit.
Thanks a lot, Jan. In the interest of time, I think we'll get to the next speaker. The members of the audience, please feel free to chase down Professor Gruber if you have pertinent questions at lunch break. Okay, thank you very much. Yeah.